Okay, so I want to give a sort of survey, sort of history, sort of introduction to this topic of higher order Fourier matrices. The first question is, what is it? And it's not particularly well defined. You can certainly argue about what is and what is not higher order Fourier analysis. So here's sort of some kind of an attempted definition. It's where you study problems in additive combinatorics or in number theory, additive number theory, using some kind of a polynomial phase or generalized polynomial phase. And so it's usually will involve somewhere, either quite explicitly or somewhere in the background, the Gowers norms and inverse theorems for them. So in my talk, I'm going to be talking mainly about discrete versions of this. But there's also very much an ergodic infinitary side to it that we'll also be hearing about a few times during this workshop as well. And I'll also be talking a bit about that in my talk too. So what is a Gowers norm? Suppose you have a finite abelian group G, and usually I'll be thinking of this as the cyclic group Z mod NZ, or as the vector space over finite fields, so fix a prime P and look at FP to the little m. There's interesting stuff to be said about other groups as well, but those are the two primary examples that people think. So there is the definition. If you haven't, I expect most people have seen this before, but if you haven't, it's maybe looks a little bit complicated. So that's the UK norm. There's one of these norms for each integer k greater than or equal to 2. And it's kind of an average of f over parallelepipeds of dimension k with some complex conjugates. So it's best, I think, if that's the definition of the objects appearing there. But I think the easiest way to understand this is just to look at the formula for the U2 norm on the bottom. So you can see it's an average of products of f with some complex conjugates over parallelograms, which are two-dimensional parallelepipeds. Now, as I've written it, it's not even obvious that it's well defined, but it's a fact that's not trivial, that the expression in brackets there is a non-negative real number, and therefore there's a uniquely defined non-negative real 2 to the kth root, and that's what the definition of the norm is. So it's well defined as a number. It's also not obvious that it makes sense to call it a norm. So that is also true. So it satisfies the triangle inequality. And it also satisfies that it's 0 if and only if f is 0. So the triangle inequality is not trivial at all. But as with the proof that the quantity in brackets is non-negative, it's just a load of applications of Cauchy-Schwarz. So I won't go over that now, but that's all true. So the U2 norm, as we'll see in a moment, is not really higher order Fourier analysis. That is classical Fourier analysis. Higher order Fourier analysis starts with the U3 norm. And just to be explicit, that's the definition of the U3 norm. I take the product of f over the 8 vertices of 3-dimensional parallelepipeds in your group, and then take the 1/8 power. It's kind of a sum over 3-dimensional parallelepipeds. So here's another way of sort of, I suppose, motivating why would you think about the Gowers norms. If your function f happens to be a phase function, so if it happens to be e to the 2 pi I times phi of x, where phi is some real valued phase, then the 2kth power of the Gowers norm is basically a kind of average of the k-fold derivatives of that phase, the k-fold discrete derivatives of that phase. And I think that makes it look sort of a reasonably natural thing to consider. Okay, so that's the definition of Gowers norms on finite abelian groups. When you're doing number theory, so if you want to do something with the primes or with sets of integers, you need to consider Gowers norms on segments of the integers. And just to be clear about what that means, because of course the numbers 1 up to n are not quite a group, to define the Gowers norm there, what you do is you sort of embed 1 up to n into a suitable cyclic group. So here, take some n primed, a bit bigger than n, it's usually convenient to take it to be a prime number. And then you define the Gowers norm of a function on 1 up to n by referencing the Gowers norm on that group, and then normalizing by the Gowers norm of the characteristic function of 1 up to n. So it doesn't matter which n primed you choose, the norm comes out the same, the normalizations kind of cancel. And the reason you do that is so that you get to say, if you've got a one-bounded function f, then its Gowers norm is bounded by 1. And equality can occur. I think that's clear. If I take f to be just the constant function 1, then equality occurs. And a nice exercise using the formula for the Gowers norms of phase functions that I showed you on the last slide is to show that equality occurs here if and only if f is a phase function. So it's got to have absolute value 1 everywhere. So it's got to be writable as e to the 2 pi I phi of x. And that phase function has to have vanishing derivatives of order k, and is therefore degree k minus 1 polynomial. So much of the sort of inverse theory of Gowers norms is concerned with the question of what if you try and relax this situation. So that's when Gowers norms are exactly equal to 1. And what can you say if the Gowers norms are not quite equal to 1, but close, so bigger than some constant or something like that? But before I come to that, let me just talk a bit about why you'd consider these things. I mean, the definition is itself somewhat natural, but I don't think that's the main motivation. The main motivation is that the Gowers norms can be used to control the behavior of pretty general sorts of linear and other kinds of patterns in sets of integers. So this is via what we call generalized von Neumann theorems. And in particular, well, the most prominent kind of example would be arithmetic progressions. And so here's a particular theorem that is sort of a consequence of a generalized von Neumann theorem. So suppose you've got a set A in some finite abelian group G. It's got density alpha. Actually, so here I'm thinking specifically about Z mod n. It's got density alpha. How many k-term progressions does it have? Well, a random set has about alpha to the k n squared progressions. And this theorem says that if you deviate from that expected value by a reasonable amount, epsilon n squared, then the Gowers norm of essentially the characteristic function of A, so what we call the balanced function fa, is large. So that's a consequence of generalized von Neumann theorem. The way these things would usually be stated is in terms of an operator. So you might consider something like T of F1, F2, F3, and F4 to be the average value x T. So the average value of the product of the F's over 4-term arithmetic progressions. And then the usual statement of one of these generalized von Neumann theorems is that that average is bounded by the Gowers norms of any one of the F's, provided the functions F are bounded by 1. And the key thing is that it's the U3 norm that's relevant. There's a highly generalized von Neumann theorem. It says for essentially any linear pattern, provided it's what we call finite complexity, so it's not allowed to have 2 copies of the same function, essentially, there will be a Gowers norm that controls the behavior of it. Now, obviously, this is not quite the same as this. But you can go from this sort of a statement to that sort of a statement with relatively elementary sorts of manipulations. So these Gowers norms, they are themselves systems of linear forms, and they're kind of universal amongst all linear forms. So they're the only ones that you really need to consider if you want to understand the behavior of linear forms in subsets of groups. So they come up in particular when studying arithmetic progressions in the primes, if you want asymptotic formulae, or even just to prove they exist, or in studying Summer-Ady's theorem. So those have been the most prominent places where Gowers norms have come up. Any questions so far or objections? Nothing controversial said so far, I think. Let's get to the history bit. Right, so far, I mean, I haven't actually done anything, of course. I've stated a few things, kind of. But the maths underlying everything I've said so far is just the Cauchy-Schwarz inequality. And to really be doing higher order Fourier analysis, you need to go a bit beyond Cauchy-Schwarz, although you still do a lot of Cauchy-Schwarz. And that happens where you link these Gowers norms to actual polynomials or similar things via what we call inverse theorems. And an inverse theorem is a result of this type. So if the Gowers norm of some function is on the order of 1, so just I've been a bit lazy with my notation here. So this means it's going to mean the same thing as suppose the Gowers norm is at least some delta, where I think of the delta as a fixed number. Also, sometimes we talk about UK norms. Sometimes I talk about US plus 1 norms. The reason we tend to write US plus 1 is that that's the norm that's linked to degree S behavior. It's sort of convenient way to write. So an inverse theorem is any kind of result of this type. So the Gowers norm of a function is large, close-ish to 1, if and only if the function has some degree S behavior, actually related to some algebraic degree S object. So the U2 norm is not higher order Fourier analysis. That's traditional Fourier analysis. And let me just recap what the inverse theorem is there. Could have been proven in the 19th century if people had sort of had talked in this sort of language. So the inverse theorem for the U2 norm on a group says, suppose I've got a one-bounded function, so it's bounded pointwise by 1, whose Gowers norm is at least delta. Then it has a large Fourier coefficient. In other words, it correlates with a character on that group. So G hat is the group of homomorphisms from G to the complexes. And the Fourier transform of f of the character is just the inner product of f with the character defined like that. So on Z mod NZ, the characters are going to be of this form. And so on that group, this U2 inverse theorem is definitely saying, suppose I have a large U2 norm, then my function correlates with a linear degree 1 plate. So the only proof I'm actually going to give, this is, I expect almost everybody knows this proof, it goes via a magic formula for the U2 norm in terms of the Fourier functions. So the U2 norm of a function is the L4 norm of its Fourier transform. And the L2 norm of a function is the L2 norm of its Fourier transform. That's positive. So basically, if you just play these two off against one another, if you have large Gowers U2 norm, that implies this. The middle thing here is just an elementary inequality. And then on the right-hand side, I've applied Parseval and the fact that f is 1 bounded to bound this by 1. And if I take everything together and square root both sides, that just gives me the inverse theorem for the U2. So once you've set up the language, and I suppose you have to prove the identity at the top, but it's just a piece of algebra using the orthogonality relations. The U2 inverse theorem is pretty straightforward. Okay, so now let's talk about some actual higher order Fourier analysis. And what I call the modern era, so the whole theory really, it really started with this astonishing work of Gowers in 1997, maybe 1996, his paper on four-term progressions. Really one of the great papers. So not only did it implicitly introduce the Gowers U3 norm and prove an inverse theorem or a local inverse theorem for it, but it also introduced the Balog-Semerady-Gowers theorem for the first time. And it also sort of repopularized Feynman's theorem and introduced that as a major tool. So it's pretty astonishing what that paper did. So Gowers proved a local U3 inverse theorem, and here's what it states. Suppose I have a one-bounded function on one upper n, and it's got a large U3 norm. Then you can partition one up to n into progressions, same common difference, and reasonably long, but not that long. So size n to the delta primed, where here delta prime is a function of delta, such that f is on average quadratically correlates with quadratics on each of those. So that's the inverse theorem that I showed. And so you've got quadratic behavior, but it's a bit weak because those progressions are fairly short and the quadratics are different on each progression. So although that's a pretty powerful theorem, and it is certainly enough for Gowers to prove his famous bounds on Semirady's theorem for progressions of length 4, it's not quite what we would ideally like, because it's first of all not necessary and sufficient for having a large U3 norm. You could definitely concoct a function, just a function that is a quadratic phase separately on a bunch of progressions, would satisfy this conclusion, but not have large U3 norm in general. So it's not an if and only if. And also, well, anything that involves passing to very short progressions or short intervals is going to be, with modern technology, is going to be impossible to check for arithmetic functions like the Möbius function or Von-Mongol function, anything to do with primes. So although Gowers' result was a real breakthrough, you want a bit more.
Here, sorry, the quadratic phase functions are quadratic polynomials.
Yeah, quadratic polynomials. Actually, so you say that. So it's, if you pass to some further subprogressions, maybe not with the same common difference, you can actually make them linear. I didn't want to state it like that because I sort of want to motivate the full inverse theorem. But yeah. So what's the full U3 inverse theorem? So a global, what we call a global version. So instead of passing to subprogressions, something on the whole group, that was done by Terry and I about 20 years ago. And there we also looked at finite fields of odd order. So things there are actually easier to state. So let me state that first. So suppose P is an odd prime and you've got a function on Fp to the n. And then the conclusion is that there's actually just globally a quadratic phase which correlates with f. A quadratic phase function on Fp to the n that has an amount of correlation delta primed, which depends only on delta and p, but not on n, with the function f. And Samorodnitsky handled the case p equals 2, which is probably the most interesting, well, certainly the most interesting one in computer science. So those two together, you get things for every prime field. And the point about this is that it's necessary and sufficient in the following sense. So if you have a large Gowers norm, then you correlate with a quadratic. If you correlate with a quadratic globally, then you have a large Gowers norm. Well, the passage in between the two is quite lossy, as it's certainly as it stood in 2005. So you lose at least an exponential there. So that's the finite field case. Now, it would be natural to conjecture a similar result, perhaps, in the integers, but that turns out to fail. So there are one-bounded functions whose U3 norm on 1 up to n is large, but which don't correlate with any quadratic phase. And the easiest example to describe is a bracket quadratic phase, like this. So in fact, any quadratic phase like that will have a large Gowers norm. And if you choose alpha and beta to just be some irrationals, that independent irrationals, it won't correlate with any genuine quadratic. So Terry and I, in that same paper, actually it's published in the Edinburgh journal of some kind. Two Edinburgh journals, I forget which one. So we showed that those are enough. So if you have a function with large Gowers norm on one FOM, then it correlates with a bracket quadratic phase function. So it's not just one bracket quadratic, it's a sum of a bounded number of them. And I've thrown in some actual quadratic and linear terms as well. And so if you've got large U3 norm, there is a sort of a bounded complexity bracket quadratic phase such that F correlates with that phase. And that is also necessary and sufficient. So if conversely you correlate with such a phase, then you have a large Gowers U3 norm. So in some sense, that's the answer to the question. But it's very unsatisfactory because these bracket polynomials are very unpleasant to work with. So even understanding what their distribution is, mod 1, can have some unpleasant surprises. They can be very discontinuous and so on. But it had long been known, and particularly its work of Vitaly Bergelson and Sasha Lehmann was important here, that when you see bracket polynomials, you should be thinking about nilpotent groups. So there's a very close link between bracket polynomials and nilpotent groups. And let me very quickly show you how that works. So here is the simplest kind of nilpotent group, I think, nilpotent Lie group that isn't abelian. So that's called the Heisenberg group, 3 by 3 upper triangular matrices. And inside it's a lattice, 3 by 3 upper triangular matrices with integer entries. So the quotient of the first one by the second one is called the Heisenberg nilmanifold, three-dimensional manifold that could be identified, well, basically with a cube with some identifications. And that's because I give you, this is an arbitrary 3 by 3 matrix in the Heisenberg group. You can pre-multiply it by an integer matrix with these particular entries, where those are floor functions, to take you essentially uniquely to a matrix that has entries between 0 and 1. So as a set, it's more or less the cube with sides identified. Is the cube with sides identified. So that's a nilmanifold, and it's called nil because this Heisenberg group here is a two-step nilpotent group. So on that quotient space, on that nilmanifold, we can define a function like this. So it's well defined, modulo gamma, because of the formula on the previous slide. So I can define e to the 2 pi I of that phase, and it won't depend on which representative mod gamma I took. So we call that an automorphic function, G. And then you can get a bracket polynomial by evaluating that particular function. It's a function on G, which is invariant under gamma, or equivalently a function on G mod gamma. By evaluating that function at a particularly nice sequence of 3 by 3 matrices, you get a bracket polynomial phase. So that sort of is, that's the explanation really, I think, for why there's a link between nilmanifolds and bracket polynomials. There's actually a complete dictionary between the two. So given any bracket polynomial, you can write it as coming from a nilpotent group. So this is an example of what we call a two-step nil sequence, and that's because the Heisenberg group is two-step nilpotent. I'll remind the definition in a sec. And for the experts, what I said isn't quite accurate, at least as we normally do things, because that particular function f has some discontinuities at the edge of the cube. But I'm going to gloss over that. Sort of continuous mostly. Okay, so let's just quickly run over what the general definition of a nil sequence is. So you take a simply connected S-step nilpotent Lie group, and the Heisenberg group is a good case to think about, where S equals 2. So what that means is that if you form the lower central series, taking repeated commutators, you end up at the group 1, the trivial group with just the identity, S plus first step. Heisenberg G means that. the commutator of G with itself. So commutation removes things just above the diagonal. So you get things with zeros just above the diagonal. And this is central in G. So if you commutate again, you get just the others. That's two-step nilpotent. You can define a notion of a lattice there. So it's a discrete subgroup of G. And you can define a notion of an automorphic function. It's just a function. In practice, it will have suitable sort of continuity properties, but the key property is that it's invariant under multiplication by gamma. So an example is that one that I showed you on the Heisenberg group. And then you take a polynomial sequence. I won't give the general definition, but the example I showed you on the Heisenberg is an example of such. So a sequence with basically think matrices with polynomial entries. In practice, you'll control the degrees in certain places as well, but it's roughly what it is. And then evaluate the automorphic function at the polynomial sequence. And that's what we call an S-step polynomial nil sequence. Now, there's a lot of stuff that I'm suppressing here, and probably the most important omission is any discussion of what we call complexity. So these nil sequences also come with a complexity. And if the complexity of a nil sequence is bounded, that means that you have some control on all of the things that went into the definition. Most importantly, the dimension of the group G, but also the structure constants defining the multiplication of G. Also the smoothness properties of the function f, but crucially not anything to do with this polynomial sequence P. So the complexity is uniform in that in the polynomial. So a very baby case to think about. Maybe one could think about why just a linear phase e to the 2 pi I theta n is a one-step nil sequence. And that corresponds to G being the abelian group R, gamma being Z, and the automorphic function f of t being e to the 2 pi I t. And the polynomial sequence being just theta n. So it's maybe not the obvious generalization of a character, but it is a generalization of abelian characters. So there's a nil sequence formulation of the inverse theorem, and that's basically because, as was already known to Bergelsen and Leibman, bracket polynomials can be written as nil sequences and vice versa. So once you've proved a bracket quadratic version of the inverse theorem for the U3 norm, then you can deduce a nil sequence version, which sounds like this. So if you've got a function with a large U3 norm, it correlates with a two-step nil sequence whose complexity parameters are all bounded. And again, that's an if and only if. So just as a sort of for historical accuracy, in fact, in our theorem there, our polynomial sequence was what we call a linear nil sequence. So it's of the form a to the n for a particular a in the group, which seems as if it's a stronger statement. It's actually not, it's equivalent. So the notion of a polynomial nil sequence, which is now, I think, the sort of standard thing to consider for various reasons, was not clarified until a bit later. So a little bit of history about how nil sequences came about. It's quite interesting. So the role of nilpotent groups was understood in very closely related contexts by the ergodic community earlier. And that was very important in motivating the formulation of the inverse theorem in the discrete setting. So nil manifolds themselves were studied, maybe even the 40s, by Malchev, just from sort of almost a linear algebra perspective, so basic properties of those. And then from a dynamical perspective, they've been important examples since the 60s, well before there was any potential link to additive questions. So there it's Auslander and Leon Green and Hahn Parry are some of the key names. Anything that we could now see as potentially relating to additive combinatorics came a bit later than that, in the 1980s. And it's this work of Collins and Lecinia from the 1980s that seems to really crystallize some sort of an ergodic version of the statement that two-step nil sequences have something to do with four-term arithmetic progressions. Now, nowadays, we'd see that as going via the Gowers U3 norm. They didn't have anything like a Gowers U3 norm. But the relevance of nil sequences to some sort of ergodic analog of four-term progressions was seen by Collins and Lecinia. Although, should be said, so I looked at that paper, earlier in 1984, they'd actually incorrectly asserted that essentially a statement that's essentially the fact that if you're interested in four-term progressions, or the Gowers U3 norm in modern language, then only genuine quadratic phase functions are relevant, which we now know is wrong. And they say in their paper that the need for nilpotent groups was pointed out to them by Furstenberg and Weiss. So clearly, Furstenberg and Weiss should take quite a bit of the credit for this idea that nil sequences are relevant in additive combinatorics. And I think that's the first place in 1988 where one sees this. This 88 paper of Collins and Lecinia is extremely short. It's really just an announcement, like 2 pages. Now, once you've done something in the two-step case in the ergodic world, it would certainly be very natural to conjecture generalizations to longer progressions and higher step. I'm not 100% sure that explicit conjectures were in the literature, but it must have been in the air in the ergodic theory community. And such statements were proven by Host and Krah in 2003, and then independently by Ziegler around about the same time. And the Host-Krah work, well, it has structures in it which are really the ergodic analogues of the Gowers. So it was that work that really provides an ergodic sort of version of the inverse theorem for the Gowers norms. Now, the notion of a nil sequence itself doesn't explicitly occur in those works. That was introduced by Bergelsson, Host and Krah in 2005. But Terry and I, when we did our work on the U3 norm, had all of these things. So when I say had them all, we had all of those papers on our desk. So it's clear that the ergodic theorists really influenced the statement that we were trying to prove. It's fair to say there's no way we would have written down an inverse theorem for the U3 norm with nil sequences without all of this ergodic work being known at the time. So what about the higher UK norms? Well, the inverse theorem for higher UK norms was conjectured by Terry and I in 2006, where we showed that it, together with a statement about how the Möbius function interacts with nil sequences, was enough to understand linear equations in primes. And that theorem, that conjecture was proven by Terry and I and Tony Ziegler, first for the U4 norm and then slightly later for general norms about 5 years after that. So here's the statement. It's the same as the statement for the U3 norm, but just with the indices increased. So if you've got a large U4 norm, you correlate with a 3-step nil sequence, and so on. And again, we in fact show that this P can be taken to be a linear nil sequence, and that's how we originally conjectured things. And one reason I keep saying that is I think that makes it clear how inspired we were by the ergodic theory, because in ergodic theory, somehow these polynomial sequences don't come up so naturally, and they were always talking about the linear nil sequences. So Host and Krah, for example, are only ever talking about linear sequences. I should certainly say that Gowers had previously proven a local version of this, analogous to his local U3 inverse theorem back in 1997. So it's a similar statement to his local theorem, and it has similar consequences to Semerades' theorem, but also similar shortcomings in that it's not an if and only if condition, and you have no chance of checking it for arithmetic functions like the Möbius function. So that's just a restatement on the same slide of that theorem of Terry and Tammy and myself. And I just want to show you, as I've said, the motivation for this really came from the ergodic community. And I'm not going to define the terms appearing here, but just so you can see how closely analogous this is Hoss-Krau's main theorem, essentially. So they define this semi-norm, and it's kind of obviously the same sort of thing as the Gowers US+1 norm. It involves some parallelepipeds. And their theorem is that that is zero if and only if the projection of f, which is a function on some measure-preserving system, onto some sort of a nil system is zero. Contrapositive, if their norm is not zero, this projection is not zero, that tells you that your f has some sort of nilpotent behavior. So you can very clearly see that this is a sort of ergodic analog of the inverse conjectures. And before I move to talking, I want to talk a bit about quantitative things. Segedi and collaborators have given a different proof of the inverse theorem at the top here that is closer in spirit, I think, to this work of Hoss-Krau. So that's some sort of somewhere halfway in between, I suppose, but gives this statement, gives a discrete statement. Let me say a couple of words about finite fields. So first of all, recall the inverse theorem for the U3 norm over finite fields says if you've got a function with a large U3 norm on fp to the n, then it correlates globally with a quadratic. So that's the finite field U3 inverse theorem. And if you've written that down, it's natural to conjecture the same thing for higher norms. So it's natural to conjecture that if you've got a function with a large s+1 norm on fp to the n, then it correlates with a degree s phase. But that conjecture I'm going to say first. So why were we thinking about the finite field case? For the U3 norm, the main motivation for thinking about it was that everything is easier in the finite field setting. What goes into this are things related to Feynman's theorem. Finite field setting, Feynman's theorem involves only subspaces, not generalized progressions. Everything's much cleaner. And so we thought of it very much as a model for the integer case. But it turns out for the U4 norm and higher, it actually misled us, really. It turns out to be harder to deal with these finite fields. And it has acquired kind of a life of its own. So yeah, the conjecture on the previous slide actually fails. So it's not true. If you've got a large s+1 norm, that was s+1 norm, then you correlate with a degree s phase in the way that I said. And there are low characteristic counterexamples. For example, over F2, and for the U4 norm, that statement fails. And the issue is kind of an algebraic one. So you shouldn't be considering these, what we call a classical polynomial phase, coming from a polynomial map from fp to the n to fp. You really need to be working with phases that can take any values in R mod z. They're the same thing in higher characteristic, or equivalent to the same thing, but they might not be the same thing in low characteristic. So that's the sense in which the conjecture fails. And I think in retrospect, I don't really know why we were so hung up on that. But anyway, here's the correct conjecture. It's just the same as before, but now I'm allowing these non-classical polynomial phases that don't necessarily take values in the Pth roots of unity, but just anywhere in R mod Z. So that was proven by Terry and Tammy, and a crucial element of that proof was an ergodic result with the two of them and Vitali Bergelsen. So ergodic theory is crucially used in this proof. And then it was extended to all characteristics with the appropriate reformulation about 3 years after that. And just to kind of complete the rectangle, so there's a sort of Segedi style proof of this with his collaborators Candela, Gonzalez, Sanchez quite recently. So now I'm going to talk about quantitative issues. Go over this fairly briefly because I want to say a few more general remarks at the end. So everything so far has been somewhat qualitative. I've not said anything much about the dependence of delta prime on delta, which is pretty crucial for most applications. So in particular, if you're interested in bounds on Semiramis theorem, it's completely critical what that dependency is. Now, this U3 inverse theorem of Terry and mine already came with somewhat reasonable bounds, kind of exponential dependencies. And then a few years later, it was discovered that the quantitative issues around this theorem are more or less equivalent to quantitative issues about subsets. So basically, if you prove good versions of Riemann type theorems, you get good inverse U3 theorems. That was already known by Gowers, and the other way around as well. So essentially, we had to wait for some advances in subset theory. But they did come along. So Sanders' work from about 2011 or so does allow for the bounds in this theorem to be improved to quasi-polynomial. So particularly the dimension of the group G is kind of just logarithmic in 1 over delta, and the delta primed is quasi-polynomial delta. Now, I should say for full accuracy, I don't think this was stated anywhere until the work of Maytab and James and Ashwin. But more or less, it follows by inputting Sanders' work into the 2005 work. Finite fields. Now here I'm starting to use colors. A color means that somebody will be talking about this very work at this conference. The recent proof of Martin's conjecture that Freddie will be talking about shortly can be input into this work of Terry and I in the finite field case and Samorodnitsky in the case B2 to actually give polynomial bounds. So we do now have polynomial bounds for the U3 inverse theorem. So if the U3 norm of a function is large in a finite field, you get polynomial correlation with a quadratic phase function. The degree of the polynomial depends only on the characteristic of the field. Some dependence will be necessary. Now, turning back to integer Gowers norms. So here's the qualitative statement of the inverse theorem for the US plus 1 norm that Terry, Tammy, and I proved in 2011. So our proof gives, I think it's sort of in principle explicit for the U4 norm in the sense that it doesn't use any ultra products, but very bad. And it gives no bounds at all for U5 and higher because it does use ultra products in that setting. So really, this is a purely qualitative theorem. And as such, it's useless for giving new bounds on Semiramis theorem or for getting explicit error terms or anything like that in understanding the primes. But then Freddie gave a substantially different argument, really quite different from first principles, which does give a quantitative bound, and his bound is a sort of double exponential. And then, as we'll be hearing this afternoon, the spectacular work of Lensar and Sawney from this year has given quasi-polynomial bounds for all of these norms. And so we now have bounds that pretty much match what we know in the U3 case. So we'll be hearing about that in 2 talks this afternoon. Now, the finite field setting. So here's the finite field inverse theorem by Tau and Ziegler. So the difference between this and the integer case is that there are no nilsequences, it's just degree S phases. But as I said, it's actually proven, so we're now in a situation where, although for the U3 norm we have polynomial bounds for this theorem, for the U4 norm and higher, our knowledge lags behind what we know for the integers, which I find pretty surprising. And I think, I may be wrong, that the state of the art is as follows. So for the U4 norm, Gowers and Luca have the best bounds for the U4 norm in characteristic 5 or higher, and then Jonathan Tidor for characteristic 2 and 3. And those bounds are of this shape. Is that correct? Or maybe your paper missed an exponential?
Well, I think that the initial version had 2 exponentials, and then Lovett in personal communication improved it to a single
Oh,
exponential.
so it is actually much better than this, is it?
Yeah, and I'll be talking on Wednesday about quasi-polynomial bounds actually. With
Oh,
the new result.
Unfortunately, I can't put you in red.
Okay, that's fine. Yeah, I changed it in the very last.
Imagine that Luca's name is in red on this thing. And also, so I guess what I might say that is probably inaccurate, but it was accurate to my knowledge. Yeah, and I think you write in your paper that if you knew the Martin conjecture, you would get some better bounds here.
Yeah, probably even one exponential then.
Okay.
Or
All right, so I think I'm just going to leave the further discussion of this to Luca because I suspect that what I've written here, although I think it's the state of the art in terms of what's published, is probably not the state of the art anymore. Is that a rough summary of what's actually?
yeah, that's true. Yeah.
So Luca will update us on this later. I think it's natural to conjecture that there is a fully polynomial inverse theorem for the US plus one norm over finite fields. I certainly don't know of any counterexample to that. And that would basically say that this delta primed is polynomial in delta with the degree depending only on the S and the P. Okay, so let me finish by just sort of, I've really dwelt mostly on inverse theorems and the state of the art there. There's been a lot of recent movements on that, as we'll hear. But let me just run through what some of the further topics in higher order Fourier analysis are. The inverse theorem by itself, it's a limited use unless you can really do something with nil sequences. And the most basic questions about nil sequences themselves, like what is their distribution in G mod gamma, in the infinitary setting where you're looking at the whole sequence, that was figured out by Leon Green. And Leon did a lot of work on polynomial sequences. And the basic finite tree result in this direction. So in other words, what can you say if some finite segment of a nil sequence is or is not close to equidistributed in G mod gamma? That was done by Terry and I in 2006. And here's roughly what it says. So it says, suppose you've got a polynomial sequence on your group, and it's not close to equidistributed in the nil manifold, then the reason for that must be that its abelianization is not close to equidistributed in this object here, which is actually just a torus. So that's projection onto the horizontal torus. So there's quite a bit more to say there, and James Leng has made really significant progress on the quantitative aspects of this, and he'll be talking about that, I assume, as part of these two talks this afternoon on the new bounds for the inverse problems. So we now understand pretty well the quantitative behavior of. So what are some other topics that I haven't addressed? Regularity, decomposition, and counting lemmas. So Julia will be talking about somewhat related to this. But the regularity lemma basically says any function can be written as a nil sequence plus a small error. That's a consequence of the inverse conjectures and is pretty useful for actually proving things. There's a lot more to the early part of the story than just the Cauchy-Schwarz inequality. I haven't said anything about that. So that's work of Tim and Julia and work of Freddie about exactly which linear patterns you can control with which norms. There's a really interesting theory there. I don't think anyone's talking about it, which is why nobody's in red here. I haven't said anything about how you can apply these sort of ideas to specific arithmetic sequences, in particular to the primes, where you're going to need versions of everything for functions that are not one-bounded, but rather bounded by what we call pseudo-random measures. And I think Terry and Yoni are going to be touching on things related to this. I've also not said anything about polynomial patterns. Sarah's in green because she's an organizer. I'm sure if she had been speaking, well, she might have been speaking about this. Who knows? I talked a bit about linear patterns, but you can actually use Gowers norms to control polynomial patterns as well, for most famously regressions with polynomial differences. And there's a whole theory there involving concatenation results proven by Tau and Ziegler, degree lowering techniques, Sarah and Sean Prendeville. And then I've also not said anything about further developments in the infinitary realm. So the world did not stop with Host and Kroll in 2003. And there'll be several talks where ergodic results will be actually used. So the talks of Alexei, Joel, and Fourier and Richter will touch upon that. So there are, I think that the sort of 5 further topics that I've said little about, but with the exception of the true complexity, I think we'll be hearing more about them. So then finally, what are some future directions and challenges? Well, I'll just name a couple. So one obvious one is a polynomial inverse theorem for the UK norm finite fields. I'd say all better bounds such as a fixed tower of exponentials. Maybe you've now done this. Have you?
Well, we don't have it for the low characteristic, but it's a fixed number of exponentials for any k for high characteristic.
Okay, so we'll be hearing about that later. But yeah, still the polynomial inverse theorem. So work of Ashwin, Mehtab, and James gives a quasi-polynomial inverse theorem for the UK norm. In principle, there could be some kind of a polynomial inverse theorem. We don't even quite know what the right statement would be. I mean, you can sort of write down things that might be plausible statements. And we certainly don't know what the right proof would be. So even for the U3 norm, this is basically equivalent to the polynomial, what we call polynomial Freiman-Ruger conjecture over the integers, which is definitely not covered by this recent work of Freddie, Gowers, Terry, and myself that we'll hear about shortly. Slightly unclear to me what the applications of that might be. I think it's sort of an interesting question, but probably the quasi-polynomial theorem is for most practical applications is as good as you need. Now here is a more, I still think, with no offense to anybody in the audience, we don't have a natural or accessible proof of the inverse conjectures. I mean, the proof in the U3 case is not too bad, but in the higher cases, all of the proofs are pretty awful, to be honest. All 4 of them. So there's the GTZ proof, Freddie's proof, Segedy proof, then the Lang-Sarsouni proof. They're all highly long and very complicated, and one feels there must be a more natural proof out there somewhere. That's always been my feeling. So that's still an open question. And then I'll finish by mentioning this whole world of higher dimensional norms. So everything here is a sort of norms on the group G, but there are norms you can define on G cross G. And this norm of defined by Tim Austin, which is counts. I think this is probably the simplest norm for which we don't have any even qualitative inverse theorem. So this is a norm for functions on G cross G. And it counts rectangles shifted by diagonal HH. So it's sort of, it looks a bit like somewhere halfway in between the 3-dimensional box norm and the Gowers U3 norm. And the conjectural inverse theorem has some features of both. So I think we probably conjecture that if f has a large this norm, then it correlates with something like a product of function of one variable or the other variable or the diagonal variable or some bilinear example. But that's just the simplest case, and that's what already you're going to need to understand this to get quantitative results about about squares rather than just corners. And of course, there's a whole world beyond that as well. So I think that's sort of definitely a big challenge. But I'll stop there.